to day 11 of calculus. Today we're going to talk about some super fundamental ideas of calculus. This chart in front of you has x as time and y as distance from breaking point. The setup is a car is driving at 30 feet per second and then puts on its brakes. So as time goes by, this is the distance from the breaking point when it started to brake. This question, first part A, asks, what is the car's average velocity over the first 2 seconds? And this is just an average rate of change question. So for the first 2 seconds, that would be from this point to this point, we'd calculate the average rate of change. So it's going from the point 0, 0 to the point 250. And the average rate of change is going to be 50 minus 0 over 2 minus 0, which is going to be 50 over 2, which is 25. And it's going to be in terms of feet per second. Okay, so that's the average velocity over the first 2 seconds. What about the average velocity over the second 2 seconds? Well, that's going to be from 250 to 476, from time equals 2 to time equals 4. So that's from time 250, or point 250 at time 2, and it's 50 feet from the breaking point, to 476. This average rate of change, this slope of the secant line is 76 minus 50 over 4 minus 2, which is 26 over 2, which is 13 feet per second. So for the second set of 2 seconds, from time equals 2 to time equals 4, the average rate of change is 13 feet per second. So the car is slowing down. Here's a question though, it's a little different. How fast is the car going at 2 seconds? And we can really only estimate this. So I'll clean this up just a little bit here. So we'd like to know how fast is it going right here? Well, the way we do that is we pick the next data point that is closest to it. In that case, that's this point right here. So what you do to find the instantaneous rate of change, or as close to the instantaneous rate of change as you can, if we want it at time equals 2, you take the next point. So we're going from 250 to 2.5, sorry, that's the x value, 2.5, 59.4. So that slope is going to be 59.4 minus 50 over 2.5 minus 2. And if you do that out, you end up with 18.8 feet per second. And that kind of makes sense because it's in between these two values. So again, to find how fast the car was going at time equals 2 seconds, we took the closest data point to 2 seconds, which was at 2.5. So how could we become more accurate? If we graph the data, we were given, here are the data points. It's the same chart before, but with a graph. What we did in the first one from 0 to 2 seconds, that's from 0 to 2, is we found the slope of this line right here, and we found that to be 25. The second one we did was from 2 seconds to 4 seconds. So that's from here, change it to blue here, here to here. We found that this slope was 13. Well, how could we make it more accurate? Well, we could get more points. We could get more points and have a smoother idea of what's going on. So the distance is increasing. It is an increasing function, but the car is slowing down. It's slowing down. The average velocity is decreasing, so therefore it's concave down. Remember, you can figure that out because the secant line, the slope of the secant lines are getting shallower. So it went from a slope of 25 to a slope of 13, that's decreasing, so it's concave down. But let's make this more general. Let's say we're at this point right here, and that's the x value of a, and we're at this point right here, which is an x value of a plus h. You've gone h units over. So this is a, comma, the function evaluated at a, and this is a plus h, comma, f of a plus h. So we're generalizing this. We're starting at an x value of a and we're moving over h units. So what's the average rate of change over that interval going to be? Well, it's the same idea. You take the slope between these 2 points. We find this slope. So that's going to be f of a plus h minus f of a over a plus h minus a. So just to be clear about where those come from, there's the there's this, f of a plus h, and then we're subtracting from it f of a right there. And then we have these two values, a plus h right there, and then there's the purple right there. So let's simplify this a little bit. What does this turn into? Well, m turns into, the top stays the same. You can't do anything to that, but look what happens on the bottom. You have a plus h minus a, that's just h. So this is important because we asked a question up here on C. How fast was the car going at time equals 2 seconds? To estimate that, we picked the point as close as we had to 2. But let's say we want to make that more accurate. Remember I said before, more points would give us an idea of a more accurate instantaneous rate of change. So let's go back down here. If we wanted to know what the rate of change was right here, this slope would be an estimate. But to make it a better estimate, we would want to bring this point closer. We would want to make h get smaller. H goes to 0 and take this one, and then this one, and then eventually we'd find the slope right here of the tangent line. You want to bring this point closer. This one is anchored, but you bring the right one in. You make h get smaller. Get h smaller. So what you're doing is you're taking h and you're bringing it to 0, and you're looking at what happens to f of a plus h minus f of a over h. And we know what we're looking at really is a limit. There we go. This is the instantaneous rate of change at x equals a right there. To write it out nice and pretty like, we're calling this the definition of derivative. The derivative of the function at a, the instantaneous rate of change of the function at a. The function f at a is going to be the limit as h goes to 0 right there of f of a plus h minus f of a over h. H is going to 0. Another name for this is the difference quotient. Oh, you really can't see that. The difference quotient. The difference quotient. So this is the definition of derivative. Hey, we have a definition of derivative now, which is the instantaneous rate of change at x equals a. This limit represents the slope of the tangent line at the point a, f of a. So over here, as we brought this point right here closer, that point closer, we brought it this way towards here. We're ending up trying to find the slope of this tangent line. Remember, tangent means touching. So if a point is here, this would be the tangent line, something that touches once. That's the tangent line right there. So the derivative helps us find that. And we can write the derivative right now as a limit. And in this case, it's called the difference quotient. So let's practice this. Suppose a person is walking along a straight path and his distance from home is given by f of t is 2 to the t, where t is in seconds, f of t in feet. Find his average velocity. So this is just, remember, finding the slope between 2 points. And this is an interval from t equals 2 to t equals 3. That's what this means. So what are these points? We're going from 2, 2 to the 2, because that's the function 2 to the t. We're going to 3, 2 to the 3. So that point right there is 2, 4. And this point right here is 3, 8. So what is the slope between these 2 points? Well, it's going to be 8 minus 4 over 3 minus 2, which is 4 over 1, which is 4. And let's make sure we put units on it. So that's going to be 4 feet per second because it's a velocity. Nice. What's the instantaneous velocity at t equals 3? Well, the first thing you're going to write down when you see instantaneous velocity is you're going to write down this limit. Limit as h goes to 0 of f of a plus h minus f of a all over h. Yes, you need to memorize this. In this case, our function is f of t is equal to 2 to the t. That's our function. So what is this limit going to look like? Well, it's going to be the limit as h goes to 0 of 2 to the t plus h minus 2 to the t. So that's the function. And you can write it as a. I mean, if it's a little bit more consistent in terms of terms, you could write it as a, or you can keep it as t. For now, let's decide to go with t, but with the definition being a is where you're taking the derivative. A is where you're taking the derivative. So let's do this out. The first thing we need to identify is what is our a value? Well, it tells us the a value right here. It says at t equals 3. So that is going to be our a value. So we're talking about f of 3 plus h minus f of 3 over h. And our function is 2 to the power, 2 to the power. So whatever you plug in, it's 2 to that power. So now we have the limit as h goes to 0 of 2 to that power minus 2 to 3 all over h. So now we have this nice limit right here. We'd like to know what happens as h goes to 0, as h goes to 0. And you look at that, and as you remember, the first thing you check when you're evaluating limits is, can you plug in the c value? Can you plug in this? Can you plug in that 0? You can't, because then you'd have a 0 in the denominator. Maybe there's some algebra you could do. You could factor out maybe 2 to the third, and you get limit as h goes to 0, 2 to the third times 2 to the h minus 1. all over h. Nothing cancels. This h is still there. So you are going to need to use a table for this. You will need to use a table. And we want to get really close to 0. So let's go 3 on each side. 3 on each side. So let's go close to 0. So how about 0.001, 0.01, and 0.1, and then going the other direction, negative 0.1. So we've gone in both directions. So these are the x values. So in this case, the h value, because h is going to 0. And what is this function going to be if this right here is f of h right here, f of h, the function in terms of h. So now we need to use our calculator to do this. So now we have our calculator. You just have to be very careful about plugging in the function properly into y1. If you write it out in one line, it looks like this. Make sure you use the proper number of parentheses. Remember, 2 to the third is 8. So if I type that into my calculator, it looks like this on my calculator, and on yours, some of yours, it will look like this. You might have to put in extra parentheses around this if it doesn't go into the exponent, but make sure you type it in like this. But once you type it in and evaluate it, so when you do this out, make sure you use judicious use of y1 and the second entry button, and you can fill in these decimals. So now that we've filled in it looks like what's going on here. So as you approach from the left, there's this way, and as you approach from the right, what do you get really close to? Well, you look at your middle two values here, 5.543 and 5.547. And what's right in between them? Well, you can add them together and divide by 2. So 5.543 plus 5.547 and divided by 2, that's going to be 5.545. So that's our estimate for this. This limit right here is 5.545. And we had to do it with a table because we couldn't do it algebraically. So how do we do this graphically? Well, the function that we're modeling is 2 to the t. What does that look like? If we graph this function, 2 to the 0 is 1. So it's 2 to the 2. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. So it roughly looks like this. It's like it's a little too straight right there, right? It's going to be a curve. It's going to be a pretty steep exponential curve. And what are we doing? We're doing the slope at x equals 0. Sorry, x equals 3. Remember, it's at 3 right here, at 3. So what's that slope at 3? 1, 2, 3, right about here. So if you did this out, what would this slope be? And what did we find out? We got that slope. It's a little bit exaggerated here, but it's 5.545. It looks like that's the slope right there when x is equal to 3. Or in this case, we called it t is equal to 3. So if I graphed it more accurately using my calculator, it looks like this. And then if I go to the graph where t would be 3, go up to here, so that's the point where t equals 3, and we know it's 2 to the t, 2 to the 3 is 8. So when you plug in 3, so this point right there would be 2. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, looks like it's about 8. If you drew the tangent line, it's going to look like this. Touches once. We just calculated that slope to be 5. That slope to be 5.545, and that was the number right in between these two, right there.